In this video, I am explaining about bivariate continuous random variables. So I have already uploaded a video on continuous random variables. There I have defined what is a continuous random variable. So let us just recall the definition of one-dimensional continuous random variable. So one-dimensional continuous random variable takes fractional values as well, and values cannot be arranged in the form of sequence, whereas discrete random variable takes only whole number as its values. Continuous random variable can take fractional values, and you can't arrange the values of the random variable in the form of a sequence, because in case if the random variable taking values from 2 to 3, then there are uncountable number of reals in between 2 and 3, like 2.1, 2.01, 2.001. So that way, so you can't arrange the values of a continuous random variable in the form of a sequence. So that's why the probability distribution of a continuous random variable is named as probability density function, and it is represented by f of x. So any function f of x satisfying these two conditions is called as probability density function. The first condition is f of x must be greater than or equal to 0. As it is a probability function, each probability must be greater than or equal to 0. And the second condition is integral over r I have defined in the previous video, means given range. So given range here all real values, that's why minus infinity to plus infinity f of x into dx must be equal to 1. That means sum of all probabilities over all real values must be equal to 1. In the case of continuous variable, summation is taken with the help of integration, because it is the summation over a range of values. Whereas in the case of a discrete random variable, we were representing using the sigma notation, because it was summation of individual values. Here we are not taking the individual values, but we are taking over a given range. So here the given range is the reals, so it is integral from minus infinity to infinity f of x into dx, which is equal to 1. In the case of discrete variables, we had the probability distribution is calculated for each and every value of random variable. That we don't do here in the case of continuous random variable. That is because there are uncountable number of values between any given range. So you can't sit and get the probability of each and every value. Even if you do that, the chance is very, very small. It is almost close to 0. This is all about the one-dimensional continuous random variable. Now, bivariate continuous random variable means it is two-dimensional. Here, two continuous random variables are associated with the same random experiment. Then such variables are called as bivariate continuous random variables. A bivariate continuous random variable is denoted using this ordered pair x, y. Now, this represents a point x, y in xy plane. XY plane, we know that it has x-axis, y-axis and the origin. Now, values of random variables represents points in this xy plane. Whereas in the case of discrete random variable, they are just representing discrete values, because as they are not continuous random variables, so they represent just the points, not points in plane. These represents points in plane because they take fractional values also, hence it covers the whole plane. Now, example for bivariate continuous random variables are, see the first case. In a statistical survey, if X denotes the number of hours a child watches television and Y denotes the number of hours he or she spends on studies, then X, Y together forms bivariate continuous random variable. Continuous because child number of hours a child watches television, so number of hours may take whole number as value or fractions also as values. One more example, suppose a gun is aimed at a certain point. You take it as origin of this coordinate system. Suppose actual hit point is any point x comma y in a circle of radius 1. So if this is gun is aimed at this point, so when you shoot it need not exactly go to this point. So what we take? We take the possibilities. Actual hit point can be any point, anywhere, maybe here, here, here. Anywhere within, we will take a range for that. Range is nothing but circle of radius 1. Okay, it may be somewhere over here, may not be far away from this. That's why I have taken a circle of radius 1. Then all these points x comma y corresponds to the bivariate continuous random variable, that is set of all points x comma y such that this is the condition of a circle, unit circle, x square plus y square less than or equal to 1. Then this forms a bivariate continuous random variable x comma y, because it takes not just whole number as values, it takes fractional values as well. This is an example for bivariate continuous random variable. So in the case of bivariate random variable, especially continuous random variable, it gives you always a region in plane. So this is a region, that region is circle. In the case of discrete variables, you won't get a region because you don't have continuity there. They take only whole numbers. You have to jump from one point to another point. Whereas in the continuous case, as it takes all values, hence you will get a region or area. This is area of a circle. Within this circle, you will get a hit point when a gun is aimed at a certain point. Similarly, if x comma y assumes all values in the rectangle with these a, b, c, d as its vertices, then this forms a bivariate continuous random variable, because this gives you area within rectangle. So that is like this. If you have the coordinate plane, that's why a bivariate continuous random variable always represents a point in xy plane. So with the, suppose here you have A and B, here you have C and D, then you have to form a rectangle like this. This is the, then x comma y represents a point within this rectangle. It takes whole values as well as fractional values. Therefore, it forms a bivariate continuous random variable. Now, if you want to calculate probability distribution of bivariate continuous random variable, then we have, for a continuous random variable, probability is calculated using probability density function. In the case of bivariate variables, you have three kind of density functions. One is joint probability density function, another is marginal probability density function, one more is conditional probability density function. This gives you the probability distribution of bivariate continuous random variables. Let us see all these density functions one by one. Now let us see what is joint probability density function for bivariate continuous random variable. So this is the joint probability density function for one-dimensional random continuous random variable. So as per the definition of probability density function, f of x is denoted, small letter f of x denotes the probability density function. A function, any function satisfying these two conditions can be called as probability density function. Here integral is over the given interval or given region R. So if it is the entire real line, then you will get minus infinity to infinity. If you want to find out probability like this, p of x greater than a less than b, then you will be writing integral from a to b f of x into dx. Here we don't have the probability distribution table as we had it for the discrete random variable. That we don't do here because we are not finding the value of probability at each and every individual discrete points. Here it is a continuous random variable. We are finding the probability over a given region. Similarly, now the same concept applies here, but the variable is bivariate. So x comma y is the bivariate continuous random variable. Its probability density function is denoted as f of x comma y, one variable extra here. And any function satisfying the two conditions, which are, the first one is f of x comma y greater than or equal to 0, and the second condition is integral from minus infinity to infinity and minus infinity to infinity, another integral f of x comma y dy into dx must be equal to 1. So this is called as double integral. Integral is from minus infinity to infinity. That is because over the entire real line. So you know that R is the real line. Then here you have 0. To the right of 0 you have all positive reals. To the left of 0 you have all negative reals. So this goes up to plus infinity. This goes up to minus infinity. So all real values represented as minus infinity to infinity. Here also minus infinity to infinity. F of x comma y dy into dx. This first integral is with respect to y and the second integral is with respect to x. This is called as double integral, and the value of this double integral must be equal to 1, and value of the function f of x comma y, two variable function here, it should be greater than or equal to 0 for all values of x and y. Then such function is called as joint probability density function. To say any function f of x comma y as joint probability density function, these two conditions must be satisfied. Hence that function is called as joint probability density function. See here the first problem. Let x and y be two random variables. Then for f of x comma y, which is equal to, given by these two values, if x is in between 0 and 4 and y is in between 1 and 5, the function is k into xy. If x and y are in between any other values, then the function value is 0. To be a joint density function, this is a joint density function and these two are continuous random variables. What must be the value of k? So here they had given you it is a joint density function. To say any function as joint density function, the conditions to be satisfied are f of x comma y must be greater than or equal to 0, and the second condition is integral from minus infinity to infinity, joint density function here, minus infinity to infinity, f of x comma y dy into dx must be equal to 1. Sum of all probabilities over all real values of x and y must be equal to 1. So let us make use of this function because it is already given, it is joint density function. So if it is a joint density function, it satisfies these two conditions. So now here how the function is given. So 0 to 4 and 1 to 5. So 0 to 4 the function is kxy and 1 to 5 the function is kxy. If the values of x and y are in this between these two ranges, then the function is kxy. In all other cases the function value is equal to 0. Here also the function value equal to 0. Therefore we have here from minus infinity to infinity, but minus infinity to 0, I will split it like this. For x minus infinity to 0, the function is 0. Then 0 to 4, the function is kxy. Then 4 to infinity. So it is splitting is like this. First let us get the limits for this integral. X limits are minus infinity to 0, then 0 to 4, then 4 to infinity. Why I have written up to 0? Because here the lower limit is, the condition for x you have to see, its lower limit is 0, then 0 to 4, then 4 to infinity. In these two cases function value is 0. So anything into 0 it becomes 0. So whatever may be the other values we don't consider, we'll just write 0. Only for 0 to 4 the function is kxy. Similarly, this is for x. Now, similarly for y, here I'll split it as minus infinity to 1. Okay, minus infinity to 1, then 1 to 5, then 5 to plus infinity. 5 to greater than 5 function is 0, minus infinity to 1, this value here, minus infinity to 1, it is 0, then 1 to 5. So 1 to 5 here, the function is kxy. Therefore, by combining these, we will get x limits 0 to 4, y limits 1 to 5, function is kxy into dy into dx, that is equal to 1. So always remember, first you have to get the limits for the variable x and variable y. That is done now. Now it is double integration. Double integration is same as a single integration, but here you have two variables. When you are different integrating, when you are integrating with respect to y, you have to keep x as constant. When you are integrating with respect to x, you have to treat y as constant. So 0 to 4 keep as it is. Let us integrate the inner integral first. So k is a constant, it is with respect to y, so x is also treated a constant. Integral of y is y square by 2 from 1 to 5, then dx as it is 1. From 1 to 5 means this is the limits. Here you should have y limits, here outer x limits. So now apply the limits, then go for integration once again. So here you have 0 to 4 keep as it is, k is a constant, x is a constant, kx by 2, then y square, apply the upper limit is 5 square, 25 minus 25 minus 1, lower limit is 1 square which is 1, dx is equal to 1. So 0 to 4, here kx by 2 into 24 into dx equal to 1. This is 2 ones, 2 12s. So let us simplify this. 12 is a constant, k is a constant. So I am keeping it outside the integral. What remains in the integral? X into dx. Integral is from 0 to 4 equal to 1. So let us simplify this further. 12k equal to integral of x with respect to x square by 2. Integral is from 0 to 4, that is equal to 1. So here 2 ones are 2 6. So you will get here 6k. This is 6k. Here 4 square is 16. Okay, then lower limit 0, upper limit minus lower limit, 16 minus 0, so that is 16 equal to 1. So you will get k equal to 1 by 96. This is how to obtain the value of k. Now let us see what is this marginal probability density function. This is defined only for bivariate continuous random variable, because in the case of a one-dimensional continuous random variable, you had just probability density function. That's all. No marginal density function, no conditional density function. Marginal probability density function, there are two types now. One is marginal probability density function of x and marginal probability density function of y. So marginal probability density function of x is given by f of x, which is equal to same as you had in the case of a bivariate discrete random variable. We are taking the probabilities individually. Here also marginal probability density function of x is taking the probability of the continuous random variable x individually. So you will have minus infinity to infinity the function f of x comma y with respect to y. It is a density function of x, but integration is with respect to y. As you had in the discrete case where we are taking the row sum, there we are changing the columns. In the same way, here while taking the probabilities of this function with respect to x, here we are integrating, taking the sum with respect to y. This thing you have to remember. This is called as marginal probability density function of x. Similarly, marginal probability density function of y is denoted as f of y. Integral is from minus infinity to infinity f of x comma y into dx. Now, in the case of PDF for y, it is x. In the case of PDF for x, it is y. And it is not double integral, it is single integral because we are finding individual probabilities. This is called as marginal probability density function. Now see the second question. If the joint PDF of a two-dimensional random variable x comma y is given by, this is the joint probability density function. You have to find marginal density function, conditional density function, and you have to check for the independence of x and y. Let us do this one by one. The first one is marginal density function of x and y. So first let us find out marginal density function of x, which is denoted as f of x, equal to, integral is from minus infinity to infinity, f of x comma y into dy. Dy here because it is with respect to, it is marginal density function of x. So I already told you in the previous problem, first you have to finalize the limits now. So how to finalize the limits? See here, x is greater than 0, less than 1. And y is greater than 0, less than x. But in turn, x is less than 1. So, therefore, limits on x are, x limits are nothing but greater than y, less than 1. So, y limits as given limits directly greater than 0, less than x. Only x limits you have to write like this because it is given that x is greater than 0, less than 1, y is greater than 0, less than x. Therefore, x is greater than y, less than 1. These limits come for x. Y limits are this. So here you need dy means these are the limits of y. So this is equal to, y limits are now 0 to x. I'll write directly here. And function you have to take it as 2 into dy. So other values I have not taken. It is from minus infinity to infinity means minus infinity to 0, then 0 to this value x, then x to plus infinity. It will go like this. At all these values the function is 0, and if x is in between 0 and 1 the function value is 2. That's why I have taken integral is from 0 to x. Actually integral is from 0 to 1, then 1 to infinity, but x is in between 0 and 1, so I'll write y limit in terms of x into dy. This is equal to 2 is a constant. Integral of 1 with respect to y is y, 0 to x. So apply the limit 2 into upper limit x, lower limit 0. So which is equal to 2x. So this is the marginal density function of x. Similarly, marginal density function of y, it is denoted as f of y. Integral is from minus infinity to infinity, f of x comma y into dx now. So now you need limits of x. X limits are from y to 1. So I'll directly write from y to 1, rest all minus infinity to 0 like that, minus infinity to y, y to this. Only the function value exists in between these two limits, rest all the function value is 0. So you can directly ignore that and you can directly write y to 1, f of x comma y is 2 into dx. So this is equal to 2 is a constant. Integral of 1 with respect to x is x. Limits are from y to 1. So this gives you 2 into upper limit is 1, lower limit is y. upper limit minus lower limit. This is the way of evaluating definite integrals. So you will get f of y as 2 into 1 minus y. These are the marginal density functions of x and y respectively. See here in this problem, for the limits of x, don't take 0 to 1. Integral is not from 0 to 1. That is because we are writing it in terms of y to 1. It is a function of y, means finally you should get a function with the y as its terms. So that's why we have taken here limit y to 1. And when you are integrating with respect to x, means x limits you have to put. X limits are not directly 0 to 1 because x is greater than y and less than 1. Limits of x must be in terms of y. At least there should be one limit, either upper or lower, in terms of y. Similarly, here also it is integrating with respect to y. So, y limits are 0 to x. It is a function of x, therefore, one of the limit must be in terms of x. That is already here. Here there is no problem. It is from 0 to x. But in this case, don't write 0 to 1. You have to write it as y to 1 because it is a function of y. At least one limit should be in terms of y. Now about conditional probability density function. Suppose you have a bivariate continuous random variables x and y with the joint probability density function f of x comma y. This is a joint PDF. Now you have to define conditional probability density function of y given x equal to x. This is the condition. For this, you have to define the conditional probability density function, which is denoted as f of y given that x, which is equal to f of x comma y divided by f of x. So this is the definition of conditional probability density function for a bivariate continuous random variable. So this is the joint probability density function. F of x is the marginal probability density function of x. Condition is f of x should be greater than 0. This should be positive and it should not be equal to 0. Similarly, conditional probability density function of x given y equal to y. So that is defined as, here you have to change f of x given that y equal to y. This numerator remains same as per the definition of conditional probability. P of A given B has occurred means P of A intersection B by P of B, same way. This remains same. Here you have to change it as f of y because which condition is given, that marginal probability density function you have to write, where f of y is the marginal probability density function of y and the condition is f of y must be greater than 0. So these two are called as conditional probability density functions. One is f of y given that x equal to f of x comma y divided by f of x. Another is f of x given that y equal to f of x comma y divided by f of y. The conditions are f of x must be greater than 0. Here f of y must be greater than 0. This is the marginal probability density function of x. This is marginal probability density function of y. This is how to define the density functions for bivariate continuous random variables. Now about stochastic independence of two continuous random variables, or else you can say just when two random variables are independent. So we know that f of x given y is the conditional density function of x given y, and f of y given x is the conditional density function of y given x. These are conditional density functions. Therefore, two random variables are independent, then f of x given y is same as f of x and f of y given x is also same as f of y. Means one variable will not affect the other continuous variable. Then such variables are said to be stochastically independent. So we have the definition of conditional density function as x given y equal to f of x comma y divided by f of y. So when you apply this condition in here, you will get this implies f of x comma y equal to, this is nothing but same as f of x. If the variables are independent, then f of x given y is same as f of x. Therefore, you will get here f of x into f of y. So, f of x comma y is cross multiplying f of x into f of y. So, this is the condition for two continuous random variables to be stochastically independent. The joint probability density function equal to the product of their marginal density functions. Then we say that the two random variables are stochastically independent or just independent. Now first, conditional density function of x given y. So conditional density function of x given y. Y is in between this values, you have these values 0 and 1. These values you have to write because y equal to particular value not given here. So conditional density function of x given y, so y is in between 0 and 1 because y is in between 0 and x, but x is less than 1 means y is also less than 1. So it is denoted as f of x given y. What is the definition? F of x comma y divided by f of y. So f of y means it is the marginal density function of y, which we found just now. This is equal to, if y is in between 0 and 1, what function you will choose? F of xy is 2. 2 divided by f of y. We calculated f of y as 2 into 1 minus y. So 2 into 1 minus y, this cancels, you will get 1 by 1 minus y. Similarly, conditional density function of y given x. X is in between 0 and 1. This is denoted by f of y given x, which is equal to f of x comma y divided by f of x. F of x is the marginal density function of x. And here f of x comma y, if x is in between 0 and 1, what function you will choose? Joint density function is nothing but 2. So 2 divided by f of x, just now we found in the previous problem, that is f of x, marginal density function of x, we got it as 2x. So 2 by 2x cancels, you will get 1 by x. So this is the conditional density function of y given x. Next, last one, you have to check for independence of x and y. X and y are independent if f of x comma y equal to f of x into f of y. Joint density function is equal to the product of marginal density functions. This is very clear. F of x comma y equal to 2 for these values. If x and y are within this range, f of x comma y is 2, and for the same range we got f of x as 2x and f of y as 2 into 1 minus y. If you take the product of these two, f of x into f of y, 2x into 2 into 1 minus y, so which is equal to 4 into x into 1 minus y, which is not equal to this 2 clearly. Therefore, x and y are not independent random variables, because we didn't get the product of these two equal to f of x comma y. Hence, these two variables are not independent. Now, let me summarize the probability density functions for bivariate continuous random variables. There are three probability density functions. One is joint probability density function. Joint probability density function is denoted as f of x comma y, which satisfies the condition f of x comma y must be greater than or equal to 0 for all real values of x and y, and this integral from minus infinity to infinity, another integral f of x comma y dy into dx, this integral should be equal to 1. Then we call such function as joint probability density function. Next one is marginal probability density function. Marginal PDF. This exists only for bivariate random variables. This is denoted as f of x. Marginal PDF of x is denoted as f of x, which is equal to minus infinity to infinity f of x comma y. Integral is with respect to y. Similarly, marginal probability density function of y is denoted as f of y minus infinity to infinity f of x comma y into dx. These are marginal density functions. One more is, I'll write here, conditional probability density functions. So first one under that it is f of x given y equal to f of x comma y divided by f of y, and another is conditional density function of y given that x equal to x, which is written like this, which is equal to f of x comma y divided by f of x, provided f of y and f of x both are positive. So this is how we define the density functions for bivariate continuous random variables. Now see what is bivariate continuous distribution function. See, in the one-dimensional case, the continuous distribution function is given by f of x. Capital F of f refers to distribution function, which is equal to probability of x less than or equal to x. Means sum of all probabilities up to x including x. Here we take summation by integration because it is a continuous random variable. It takes all real values. Therefore, as per the definition of continuous distribution function, integral is from minus infinity to x, f of x into dx. This is with respect to one-dimensional random variable x. The distribution function is defined. Now, analogous to this, the bivariate continuous distribution function is defined as bivariate continuous random variable is denoted like this, ordered pair x comma y. Now its distribution function I want, distribution function. So distribution function is denoted using capital letter f of x comma y. This is equal to, so this is sum of all probabilities up to the point x comma y including the point x comma y. Here the summation is represented using integration. Therefore, integral from minus infinity to x, then integral from minus infinity to y, f of x comma y into dy into dx. The double integral is used, where f is the joint probability density function. So here both definitions are similar, but here one more extra variable, that is phi. Hence double integral, and integration is first taken with respect to y, then it is taken with respect to x. So that is how to do the double integral. So this function is called as the distribution function for the bivariate continuous random variable. So this gives you sum of all probabilities up to the point x comma y including the point x comma y. Now next is bivariate continuous marginal distribution function. So the distribution function for one-dimensional variable is sum of all probabilities up to x including x, which is nothing but minus infinity to x, f of x into dx. Now it is bivariate, so there are two continuous random variables. So its probability density function is f of x comma y. This is joint PDF, joint probability density function. So now based on this, marginal distribution function of x and marginal distribution function of y you have to find out. So the distribution function is denoted as f of x comma y. This is joint distribution function. Now I need marginal distribution function. So marginal distribution function of x is denoted as f of x, which is equal to sum of all probabilities up to x including x. Y takes any real value, but condition is on x, that is equal to probability of x less than or equal to x, y is less than infinity. Means here sum of all probabilities up to x including x, where y varies from minus infinity to infinity. So this is represented using the integral as sum of all probabilities, means minus infinity to x, then minus infinity to infinity f of x comma y into, this is the limit for y, dy into dx. So this is the first integral and this is the outer integral, inner integral, and this is outer integral. Outer integral is from minus infinity to x because there is condition on x, then y integral remains same, minus infinity to infinity f of x comma y into dy into dx. This is called as marginal distribution function of x. Similarly, marginal distribution function of y, which is denoted as f of y, which is sum of all probabilities up to y including y. Condition is on y. X will take all values, that is probability of y less than or equal to y, x is less than infinity. X takes all values from minus infinity to infinity. So using the integral, because it is sum of all probabilities up to y including y, therefore it is minus infinity to y, then minus infinity to infinity f of x comma y into dx into dy. Now here dx first, dy next, because these are the limits of x, the variable x. So that's why I have written dx first. Whatever limits here, that variable you have to write here. So these are the limits of the variable y. So I have written dy outside. So this integral gives you the marginal distribution function of y. Now about conditional distribution function. So x comma y are continuous random variables. They are defined on a sample space. Yes. To define conditional distribution function of y given that x equal to x, that is denoted as f of y given that x has occurred, x equal to x has occurred, which is equal to probability, that is sum of all probabilities here, less than or equal to y, x equal to x, as per the definition of conditional probability. So this is minus infinity to y, f of, I will use this itself, conditional probability density function. Instead of using joint probability density function, I have already defined what is conditional probability density function. I will directly use that in the integral. Probability f of y given that x has occurred with respect to y, and this is for all x such that f of x is greater than 0. You have to take for all x such that f of x is greater than 0. So this is the definition of conditional distribution function. You can write conditional distribution function in terms of joint probability density function also, but here I have defined using the conditional probability density function itself, because it is directly available, so that you will get a single integral of this function, not the double integral. If you are using double integral, then x equal to x, that is fixed, you can represent that using the double integral. That's why I have directly used here the conditional probability density function. Similarly, the conditional distribution function of x, given that y equal to y has occurred, so that is written as like this, capital F of x given that y equal to y, so which gives you sum of all probabilities less than or equal to x, and y equal to y is fixed. So now for this I will use this conditional probability density function. This is the conditional probability density function of x given that y equal to y. So I will make use of this function now. Limits are for x minus infinity to x, f of x given that y value into integration is with respect to x, because here condition is for x, y equal to y is already given. So this integral gives you the conditional distribution function. Now I'll summarize these distribution functions. First, joint distribution function, that is for continuous variable. I will not include continuous once again, here only I will write continuous distribution functions bivariate. So joint distribution function is denoted as f of x comma y, which is integral from minus infinity to x, integral from minus infinity to y, f of x comma y into dy into dx. Here this is a joint probability density function. Similarly, next, marginal distribution function. First one is marginal distribution function of x, that is f of x equal to, integral is from minus infinity to x, minus infinity to infinity, f of x comma y into dy into dx. Here condition is only for x, but for all values of y you have to take. Similarly, marginal distribution function of y is denoted as f of y, which is equal to minus infinity to y, minus infinity to infinity, f of x comma y. Now I'll write dx first, dy next. That is the only change, because here for all values of x, then up to value of y as up to the value y. That's why minus infinity to y. This limit is with respect to the variable y. Therefore, outer differential should be dy. Here I'll write conditional distribution function. So, conditional distribution function of y given that x equal to x is denoted as f of y given that x equal to x, which is equal to integral from minus infinity to y, f of y given that x has occurred with respect to y. Here I am using the conditional probability density function. Here I have used the joint probability density function in these two cases, but here I am using the conditional probability density function, that is f of y given that x. This function I am using because x equal to x is fixed and it is integral is over y from minus infinity to y. That's why you will get a single integral here, not double integration. Here it is single integration. Now similarly, conditional distribution function of x given that y equal to y is integral from minus infinity to x, f of the conditional probability density function x given that y with respect to x. So this is the conditional distribution function of x given that y equal to y. Only in conditional distribution function we are using the conditional probability density function. Here we are using the joint probability density function in marginal distribution function as well as joint distribution function. So this is the summary of distribution function. You have to remember this while before solving the problems. See here, one more question. X comma y be two-dimensional random variables having joint density function. This is the given function. You have to find P of, first one, P of x less than 1, comma y less than 3. So as per the definition of distribution function, f of x comma y equal to probability of x less than or equal to x, y less than or equal to y. So this is nothing but minus infinity to x, integral from minus infinity to y, f of x comma y into dy into dx. So as per this, now here you will minus infinity to 1, integral from minus infinity to 3, f of x comma y into dy into dx. So this is equal to, here if x is in between 0 and 2 and y is in between 2 and 4, then only the joint density function is this. In all other cases it is 0. So minus infinity to 0, then 0 to 1 you have. 1 to 2, that is not required here because it is x is less than 1. So here I'll have minus infinity to 0, then 0 to 1. Minus infinity to 0, function is 0. So 0 to 1, minus infinity to 2, then 2 to 4 actually, but we need here up to 3 only, therefore 2 to 3, f of x comma y. In both the cases function is 1 by 8 into 6 minus x minus y into dy into dx. In the rest all cases it is 0. So let us find the integral. 1 by 8 into, integrate this 6 with respect to y, 6y minus x with respect to y, x is a constant xy, minus y with respect to y, y square by 2. Integral is from 2 to 3 with respect to x. Now let us evaluate this. 1 by 8 into 6 into upper limit 3 minus 2, that is 1, 6 minus x into again 3 minus 2, that is also 1, minus 1 by 2 into 3 square is 9 minus 4 here, 9 minus 4 is 5. So you will get here 5 with respect to x. So now you have to integrate with respect to x. 6 by 8 is a constant. Integral of 1 with respect to x is x, minus 1 by 8 is a constant. Integral of x with respect to x is x square by 2, minus 5 by 2 is a constant. Integral of 5 by 2 into 8. This 5 by 2 into 8 outside. So 8 is there in the denominator for every term. So 5 by 2 into 8 is constant outside. Integral of 1 with respect to x is x. So you will have from 0 to 1. You have to evaluate this now. This is upper limit anyway. 0 to 1 means just you will get value 1. 6 by 8 minus this is 1 by 16 minus this is a 5 by 16. Okay, this is equal to, you have to simplify this. So 12 minus 1 minus 5 by 16, that is equal to 6 by 16, which is nothing but 3 by 8. This is the answer. Similarly, second one. Now, second part is you have to find out probability of x less than 1 given y is less than 3. This is the conditional probability. As per the definition of conditional probability, so numerator is p of a intersection b divided by p of b. Therefore, x less than 1, comma y less than 3, or else you can write intersection also divided by p of y less than 3. Okay. Now we have to find out only this thing because this we already got in the first question. That is, we got it as 3 by 8. Just now we found the value. So p of x less than 1, y less than 3 equal to 3 by 8. Now I have to just calculate p of y less than 3. Later I will substitute that here. P of y less than 3 means it is the marginal distribution function of y. So as per this, p of y less than 3 and x is less than infinity. The condition on x is you can take any value, but y is lesser than 3. So as per the definition of a distribution function of y, you know that f of y equal to probability of y less than or equal to y, which is nothing but probability of y less than or equal to y, x is less than infinity. As per this, minus infinity to y minus infinity to infinity f of x comma y into dx into dy. This is the definition of distribution function of y. So as per this definition, so now I have this condition. So minus infinity to 3, minus infinity to infinity, x variables condition, f of x comma y into dx into dy. Now see the function definition. If x is in between 0 to 2, then only this is the value of the function. In all other cases, function is 0. Therefore, minus infinity to 0, function is 0. Then 0 to 2, the function is 1 by 8. That is condition for x. Similarly here for y, minus infinity to 2, function is 0. Then 2 to 4, function is this, but I need just up to 3. Okay, therefore I will have integral is from 2 to 3. Then for x, minus infinity to 0, function is 0. Then 0 to 2, function is this. Then 2 to plus infinity, function is 0. Therefore you will just have 0 to 2. So you can't directly take these limits into the integral. You have to check the condition. Here it is up to 3. Therefore, I have taken 2 to 3. You can't take 2 to 4 as limits for y. You have to see what is asked in the question. So therefore, here function is 1 by 8 into 6 minus x minus y into dx into dx. Only for these values within this range, the function is this. In all other cases, the function is 0. Whenever the function is 0, you need not calculate anything for those values. So now 2 to 3 here. Now integrate this with respect to x. 1 by 8 into 6 x minus x square by 2 minus y is a constant. Integral of 1 with respect to x is x. X limits are 0 to 2 dy. You have to practice integration properly to evaluate all this. So integral from 2 to 3, 1 by 8 into upper limit apply 6 into upper limit is 2, lower limit is 0. 6 2 is 12 minus here 1 by 2 outside, 2 square is 4. So 4 by 2 is 2 minus y is constant, x is 2 into dy. So this is equal to integral from 2 to 3. This is 10 minus 2y divided by 8. So you can keep that 1 by 8 outside. Then you have 10 minus 2y with respect to y. So this is equal to 1 by 8 into 10 is a constant. Integral of 1 with respect to y is y minus 2 into integral of y with respect to y is y square by 2. Integral is from 2 to 3. 2 cancels. 1 by 8 into 10 into upper limit is 3 minus 2. Wherever you have y, upper limit is 3, lower limit is 2. 3 minus 2, it is 1. 10 minus, here 3 square, 9 minus 2 square, 4. 9 minus 4 is 5. So you will get the answer as 5 by 8. So now this answer and this answer you have to substitute in this formula. That is 3 by 8 divided by 5 by 8. 8 cancels. You will get the final answer as 3 by 5. This is the answer for probability of x less than 1 given y less than 3. Now from this question, what you can see is there is no separate question asked on finding the distribution function, the marginal distribution function or a conditional distribution function. Instead of that, they'll give like this. So if it is in the first question, it is asked probability of x less than 1, y less than 3. From this definition, we are solving the given problem. So they have not asked here find the distribution function it is understood that whenever it is given in this way, we have to make use of the definition of a joint distribution function. Similarly, in the second one, the numerator is joint distribution function, denominator is marginal distribution function. Here we may use of the marginal distribution function of y, its definition. Therefore, as in the previous problems where we used to find out the marginal density function, conditional density function, but here it is not directly asked find the distribution functions. Here they will ask you like this, find the probability where they will give the condition. This tells you you have to make use of distribution function. That is the use of distribution functions. I hope you understood the concept. Thank you for watching.